Hello everyone, my name is Selena, and in this video I'll be presenting my video lab on projectile motion. So the purpose of this lab was to test whether physics models could accurately predict the path of a real thrown object. I found that adding air resistance to my model significantly improved the match with our experimental data, suggesting that drag is an important force. So here's the setup. We crumbled up a sheet of paper into a ball that has a mass of 2.5 grams, and we threw it while recording. We made sure the motion was kind of two-dimensional. You can also see a ruler right there, so we can calibrate the distances later. Now, just like for lab 1, I uploaded the video on the tracker. I set the points, and I had, I think, 55 data points for this one, and it created me the data which I used for the modeling. In a physics model, we would say the system is our paper ball, and our surrounding would be the gravity, earth, and the air. We use these following formulas, and I implemented them in the following code. So then, the assumption and reasoning. First, we treat the motion as purely two-dimensional, so only x and y. Secondly, we have constant gravitational acceleration, which is 9.8 meters second squared. And then we model the drag as proportional to the square of speed, so which is the standard drag model, and which points opposite to the velocity. And again, the ball is treated as a point of mass. The constant b was tuned by comparing the simulation output to our tracker data. So for the modeling, I used the code given in the lab instructions. You can see the loop, which includes my force update formula with the velocity and position update formula. In the upper lines, you can see my position and my initial velocity. B was set to 0, and then B was set to 0.005 for the drag and gravity module. The blue dots you see here is my experimental data from the tracker, and the red line you can see is the trajectory, meaning the ball doesn't actually travel as far as gravity alone would predict. And the green, almost hidden line is the gravity plus the drag model, which with B equals 0.005, which follows the experimental data so much more closely. That tells us that air resistance is a real and measurable effect for this project. Let's come to the last questions. The first one is the terminal velocity. It occurs when gravitational force equals drag force and net force is 0. In our gravity-only model, the vertical velocity keeps increasing forever, so no terminal velocity. In our drag model, though, however, the velocity approaches a limit, setting mg equal to b, which v squared, and solving. We get a terminal velocity of about 2.2 meters per second of our ball. To actually observe this, we would need to drop the ball from a much greater height, several stories above, so that we can actually reach that limiting speed. And now to the second question: what if we threw the ball straight upwards with the same initial speed of, I think I had 6.4 meters per second? How long would it take to reach the ball ground compared to our original throw? And in our original experiment, the ball had a large horizontal velocity and the moderate upward velocity, so it followed a parabolic arc, landed in under a second. Thrown up straight, it would rise and slow down, stop, and then fall the way back, which takes a long time. Adding drag makes it even longer because drag slows the ascent and also resists descent. So the answer is straight up would take longer. Lastly, the errors that could occur. So we did it manually, frame by frame tracking. It includes obviously small positional errors from precise clicking. Also, the calibration depends on accuracy, measuring from the ruler in the frame. So any error scales in our distances. We also assume the ball is a perfect point of mass, which in the reality it doesn't, because we formed it ourselves, changing its drag characteristics. But also, finally, B was chosen by just a visual inspection rather than a formal curve fit, so it's also just an approximately. So in conclusion, we found that a simple gravity-only module overestimates how far the paper ball travels, adding drag force proportionally to the velocity squared gives us a much better match to the real data. So it confirms the momentum principle implemented as step by step is very powerful and flexible truth for predicting the real world motion. Thank you for listening.